Get started. Today we are delighted to have Professor Liang from MIT to give the colloquium. The title is First Principle AI for Quantum Matter. It will be a very different style talk than the AI talk we had a couple of weeks ago. Liang got his bachelor's degree from the University of Science and Technology in China, and then he went to Penn, where he worked with Charlie King, did a number of pioneering work in topological basis of matter, and he joined Harvard as a junior fellow before joining MIT faculty. I was characterized his work, always try to pioneer something new. Sort of the hallmark of his work on the crystalline topological materials and also the Majorana and the topological superconductors that 2008 PIL set up a race for this type of work. Then he also did the topological materials classification. Then he moved on to make pioneering contribution on 2D marine materials, and recently he's getting interested in yet another topic. We are going to hear about it. And he has made received many awards, including the APS Fellow for pioneering contribution in topological materials. That's a citation. And he's the Packer Fellow. And he's also a Simons Foundation investigator. And he also received the New Horizons in Physics Prize, the Breakthrough Foundation. With that, yeah.
Really a great pleasure to speak here. I'd like to start by thanking ZX for inviting me and hosting me. So today I'm going to talk about our recent efforts in building an AI model for studying materials and even perhaps predicting material properties. Now, unlike large language model, our AI method is based on the fundamental principles of physics and, in fact, the laws of quantum mechanics. So let me first thank all my team members, Tim, Zach Lama, Pierre, Anton, Graham, and Katacha Nazara, my graduate students, and Filippo, Max, and Ahmed, postdocs. So when I joined my group about 2 years ago, each one is working on different project. But over the last year, somehow some kind of a spontaneous synchronization occurred. They're all working in AIs. And to a large extent, that was actually motivated by the work that Tony Ten did about 2 years ago. At that time, Tony was an undergrad in UK, Cambridge University, and he worked with me remotely on some using AI to solve a non-trivial problem that I'll briefly talk about. And since then, we have been working non-stop in this direction. So in condensed matter physics, which is my research area, we study all kinds of materials, such as semiconductors, magnets, and superconductors. And these materials are also basis of modern technology, from transistors in smartphones to magnets in electric motors, in electric vehicles, to superconductors used in MRI machines. Now, one of the dreams in material science is to be able to predict material properties before they are measured. Okay? And the truth, the harsh reality is that it's a long pipeline from material discovery to application. This takes typically more than 10 years. So the last material database, the space of possible materials, present a great challenge to this material by design theme. There's 500,000 inorganic compounds known to humans, and this is believed to be only a tiny fraction of all possible chemically stable materials. So when you encounter problems with a vast parameter space, nowadays it's common to think about some data-driven approach. In the same way, for example, the large language model is trained on internet text to generate texts So perhaps it's possible to take the similar approach to material discovery. Maybe you can input the vast amount of measured material properties, such as the superconducting transition temperature of known compounds. You feed that into a neural network, and you hope that maybe this can give us a prediction of new superconductors. But I want to caution that this approach may have a fundamental limitation. And this is what we know from the history of superconductivity research. Before 1987, the superconducting transition temperature of various compounds progressed linearly. But then a big phase transition happened. This copper-based superconductor was discovered, and the TC shoots up, right? Shoots up above the liquid nitrogen temperature, and now it stays as the highest TC record, at least at the ambient pressure. Now, if you look at all the superconducting materials before 1987, none of them contain copper. So this tells us that paradigm-shifting discoveries does not necessarily follow from previous intuitions, from previous conventional wisdom. Okay, so knowing the past, in terms of material science, knowing the past does not necessarily predict the reality of the future. Now, on the other hand, one thing we as physicists, we know for sure is that all kinds of material properties, okay, semiconductors, magnets, superconductors, their functional behavior all arises from the laws of quantum mechanics. All materials are made of atoms, and atoms are made of electrons and nucleus. And all these properties are emergent properties. So the strong temperature dependence of resistivity in silicon follows from the presence of energy gap in the energy spectrum. Magnetism arises largely from the ordering of electrons' spins. And in superconductors, electrons, despite their Coulomb repulsion, are able to form charge 2e pairs, and these pairs collectively condense into a single quantum state that leads to dissipationless charge flow. So, and in fact, the laws of physics is very precise that all the different materials are all described by the same Hamiltonian, which is a Hamiltonian for electrons. And all electrons interact with each other through the same force, that's a Coulomb repulsion, and all electrons interact with nuclear with the same Coulomb force, but now it's attractive. So the total energy of the system consists of nothing but the kinetic energy electrons and the Coulomb interaction. So this is what I meant by saying that we essentially dealing with one type of particle, that is electron, for a fixed set of nuclear positions, which is what different compounds correspond to. And we're dealing with one type of interaction, and all the rest is emergence. And to find the ground state of the system, in principle, all we need to do is to solve the many-electron Schrödinger equation. And also, from this solution, we get a object called the ground state, which is a quantum description of any electron system. And I want to emphasize the ground state really is a complete descriptor. It encodes all static and thermodynamic properties of the system, such as total energy, the equation of state. From how the energy depends on the position of the nuclear, we can get lattice dynamics, the dispersion of lattice vibrations, for example. And by looking at the total spin, we can infer magnetism. By looking at the off-diagonal long-range order, we can detect superconductivity. So all these properties are encoded in the ground state wave function. And there's even more, research in the last 2 decades have shown that out of the many-electron wave function, one can examine their topological structure. And this actually led to the theoretical prediction of topological states, such as topological insulators and fractional chain insulators. And in topological insulators, despite having an energy gap in the bulk, it has conducting surface states and with particularly relativistic energy momentum dispersion that was discovered here. In fractional chain insulators, the system, the material spontaneously develops chiral electrical currents at the edge, and it holds fractional excitations. Even though electron carry charge E, you can get fractional particles with charge 1/3. And Twisted played a key role in identifying the material candidate for fractional chain insulators. So once again, the ground state can give us in new phases of matter has not previously been thought before. So the real question is, for a given material, how do we find the ground state? Okay. And the variational principle tells us that if we search in the space of all possible m-particle states, and for each quantum state, we can compute its corresponding energy expectancy value. And this can be done efficiently by Monte Carlo sampling in the configuration space of 3 m-particles. Each particle has x, y, z coordinates. And in principle, then searching in the space of m-particle quantum states and minimizing this energy expectancy value will lead us to the ground state. Okay, so the challenge really is that the space of all possible states is infinite dimensional. And in fact, even for one particle in a 3-dimensional space, the possible functions of one particle state is already infinite times to the power of 3-dimensional. But if you have n particles, it's really infinity raised to the power of 3n. So we're dealing with a very high dimensional, infinite dimensional space. So that's what makes this problem hard. Now, over the course of the condensed matter physics, physicists have come up with brilliant ways of approximating the ground state wave function of a many-electron system, and the so-called independent electron theory approximates a interacting electron system ground state wave function as a determinant. This is called the Slater determinant. It's the determinant built of one particle orbitals, and this theory successfully explains the behavior of many metals, semiconductors, and insulators. And about 60 years ago, this BCS theory for superconductivity was developed. And this is a highly successful theory for conventional superconductors, such as aluminum. And here, the many-electron wave function can be written as another form, which is a Pfaffian of this function G, which describes a pair of electrons. It describes the Cooper pair, a 2-particle wave function. So what do we see that in these 2 examples, the best example of human intelligence, what physicists have achieved is an enormous compression of complexity. Right? Instead of dealing with the full complexity of an n-particle wave function, these expressions are built from much simpler building blocks, 1-particle orbitals or 2-particle functions. Okay, and in some sense, this is what the theoretical physics has always been about. What we like to do is sort of come up with the most economical description of the system, at least capture the essence of it. And I found this quote from Landau saying that with 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. Okay, and then I found this paper that people actually tried and using 4 complex parameters. Okay, not real, 4 complex parameters, and you do. Nobody can deny this is an elephant. Okay? And this is a spirit of essentially less is more, right? But of course, nowadays you can ask ChatGPT to generate an image of an elephant, and this was from a year ago. And I'll say it's obvious that the level of accuracy and level of details, really, we're going from less is more to more is more. Right? Okay, so this brings me to the subject of my talk. So we want to use neural network to deal with many-electron wave functions. And the underlying idea is extremely simple, that a neural network is a very efficient way to approximate functions, even complicated functions. And it achieves this by just composing very simple operations. Each of these lines are just the linear transformations, linear mappings, and then each of these neurons represent a nonlinear activation. Okay, so if you then feed in n-particle coordinates through such a neural network, and it can output some function psi, and there's a theorem that guarantees that if the network is big enough, in principle, it can universally approximate any function. Now, which function is a ground state wave function? This is decided entirely by the energy of the system. Right? So once the Hamiltonian of the system is specified, then for every wave function generated by the neural network, we can evaluate the energy expectation value by Monte Carlo, and then one can optimize the neural network parameters. So every network parameter corresponds to a particular wave function. By optimizing the network parameter to minimize the energy, and we can come up with the best neural network approximation of the true quantum state. Okay, and in practice, this optimization is done by the gradient descent, and is extremely streamlined with the architecture of the neural network itself. Okay. That's why this is an efficient approach. And this method has been developed for almost 10 years. And early on, we combined the neural network with Monte Carlo to study lattice models of fermions, the finite temperature. Khalil and Choya and Brian Clark and D. Law developed a variational Monte Carlo using a neural network, again, for lattice models of fermions. But a very important work that we benefit a lot from is from the Google's DeepMind, led by David Pfau. They are one of the first to develop a neural network variational method to solve many-electron Schrödinger equation in continuum space for atoms and molecules. And this is this many-electron Schrödinger equation is what I'm going to talk about today. Instead of atoms and molecules, we're going to apply it to quantum physics of matter. But before that, okay, I want to first discuss a very interesting, I think, fundamental problem, mathematical problem. This has to do with a universal approximation. Okay, now in computer science, the universal approximation theorem is dealing with functions without any symmetry constraint. However, when we deal with a system of identical particles of identical electrons, the Fermi antisymmetry it tells us the fermionic wave function has to be antisymmetric on the exchange of two particle coordinates. So if you take a general neural network, this antisymmetry is not enforced, and this will lead to problems. So instead, what we want is to develop a universal Fermi network that exactly enforces antisymmetry by design, and yet is still able to approximate any continuous antisymmetric function to arbitrary accuracy, provided sufficient network size. So, and this problem, surprisingly, has not been addressed by physicists until recently, and there's only a handful of mathematical studies. Okay, and the one approach is to use neural network to generate an arbitrary function, and then explicitly antisymmetrize over all possible permutations of particle coordinates. And the problem is that the number of permutations grows extremely fast, faster than exponential, so it's not efficient. There's a very nice work, inspiring work by two mathematicians, Chen Zhang and Lu Jianfeng, about less than 2 years ago. And they show that one can create a universal architecture by first mapping particle coordinates into a high-dimensional vector space, and this eta is antisymmetric in particle coordinates, while this g is an odd function, and this guarantees the antisymmetry. And they were able to show that if the dimension of this high-dimensional space grows polynomially in particle number with exponent that is a spatial dimension, then it's guaranteed to be universal. Okay. Now, in dimensions higher than 1, in 2 dimensions or 3 dimensions, if you think about it, that the dimension of this feature space is far bigger than n, right? So we want to construct an antisymmetric function of n variables, and this method says that you need to think about the functions in an even bigger space, parametrically bigger space. So this led me to think whether we can simplify this and to achieve the same scaling as n. Okay. So before that, let me briefly tell you a little bit about the problem of bosons, right, which is a symmetric function. Now, if you have a configuration space of, if you think about a system of identical particles, the physical configuration is actually specified by an unordered set of coordinates, R1 to Rn, not a vector in the Euclidean space of d times n dimensional. Okay, so in other words, think of this way. If you look at this image, right, this image consists of a whole collection of points. In computer science, it's called a point cloud. What this image represents is independent of which point you call the first point and which one you call the second point, etc. right? So if I want to build an image classifier, it should be a mapping from an unordered set of points into a label, and in this case, a horse. Right? So likewise, if we think about a system of bosons, the boson wave function should be a function that's directly defined in configuration space that is not the Euclidean space, but instead the quotient of the Euclidean space mod out all the permutations among the n particles. Okay, so we'll see how to do that. But for fermions, this problem is more nasty because for fermions, for a given unordered set of particle coordinates, the fermion wave function generally can take plus minus values depending on the parity of the permutation. So it's not just a function in configuration space, but it's a function in the double cover of configuration space, and it takes two possible values. Okay, so this motivated me to use the following construction, to come up with the following construction, that we want to express any antisymmetry function as a function in the space of Xi and eta, where Xi parametrizes the physical particle configurations, which is permutation invariant, while eta is an antisymmetric function that keeps track of the permutations, keep track of the parity of the permutations. So together, Xi and eta you can think of as forming a collective coordinates that parametrizes the double cover of the configuration space. So as long as f, this function f is odd in eta, then the antisymmetry is guaranteed. And achieving an odd function is easy. We can do it by, for example, explicit antisymmetrization. Okay, and in this case, the computational cost is order 1 instead of order n. Okay. So in order to make a universal representation, what we need then is that we need a Xi, this symmetric coordinates, to be an injective mapping between the configuration space to the high-dimensional vector space. And this actually has been recently shown to be possible using only a space of dimensional of order n. Okay, there was a rigorous mathematical work from last year. So the task then remains is to find these antisymmetric functions that can faithfully track the permutation, even odd permutation of any collision-free configurations. Okay, so for any configurations in which some particle coordinates coincide, then an antisymmetric function eta has to be 0, and so is the original target wave function psi. But for any non-collision configurations, then in order to have a universal representation of power, we need this eta function to be non-zero. Okay, and the functions have this property. I call it a signature encoder because it faithfully encodes the signature of the permutation. Okay, so then the question is, how do we find such signature encoders? Now, if you take an arbitrary antisymmetric function, for example, the ground state wave function of a non-interacting Fermi C, this wave function has many more zeros than required by Pauli. In a two-dimensional system, the zeros actually form lines instead of forming points. Okay, so now for students who have known a little bit about quantum Hall physics, there's a very neat wave function, which is a wave function of the complete field of Landau-level, which can be written as a product of zi minus zj, where z is the complex particle coordinates. Because it's a product of pairwise coordinate differences, this complex function vanishes only when particles coincide. It has no other zeros. So therefore, this wave function, this function can be used as a signature encoder for any electron system in 2 dimensions. So we see that only a single complex function is sufficient to do the job. And likewise, in 1 dimensions, you can take pairwise coordinate differences, the real coordinate differences. Now, in both cases, this type of pairwise products can also be expressed as a determinant of single particle orbitals, and this is a property known as the Van der Waals determinant. So the conclusion is that with this Xi eta representation, we can represent any antisymmetric continuous function using a total feature dimension that is of order n. Okay, and I've shown how it works in 1 and 2 dimensions, and it also works in any dimensions. So in 1 and 2 dimensions, the dimension required for eta is of order 1, while the dimension required for Cassini is of order n. So that's why the total dimensions order n. Okay, so I call this construction of Fermi sets because it combines both the symmetric part, which is a set, an unordered sets, with an antisymmetric part, which captures Fermi statistics. Okay. Now, one can go even further. Instead of using this fixed form of a quantum Hall wave function as a signature encoder, because this signature encoder can be written as a set of a determinant, as a determinant of a matrix, we can further promote the signature encoder to be a learnable stated determinant, meaning that the neural network can actually search in the space of all possible stated determinant with all possible single particle orbitals. And because at least for one special determinant, the universality is guaranteed, then searching in a larger space also guarantees universality. Okay. And on the other hand, the symmetric part can be produced by a permutation invariant neural network that computer science have developed, either deep sets or transformers. So the punchline is that Fermi sets is a provably universal, physically motivated fermionic architecture, and it's systematically improvable with increasing network size. Okay, so compared with traditional variational Monte Carlo method, which uses Slater-Jastrow, here we use complex valued Slater determinants, and we use complex valued symmetric factors. And also, important thing is that as we increase the network size, the variation principle guarantees that the variational energy always go lower. So that's the power of neural network. And you can see that in this proof of universality, what's really important is this notion of injectivity, that we want to make sure that every non-collision particle configuration can be mapped to different Cassini and eta coordinates. And what I find interesting that shortly after I posted my paper, I read the news. There's a new paper from computer science that came out that dealing with, obviously not electron systems, but dealing with large language models like ChatGPT. And these authors show that actually different prompt texts, okay, are mapped into different vectors in feature space. So this mapping does not involve a loss of information, but it's actually injective. And it also implies that one can reverse engineer from the feature dimension, feature space, and to recover the original. So in both cases, the injection is crucial. Okay. So this is basically what the architecture look like. We feed in particle coordinates, and there's an antisymmetric parts that builds the Slater determinant, and there's the symmetric parts, which we find that transformer is particularly powerful. This is the same transformer architecture as in large language models. And transformer is a permutation equivariant construction. You have an input, you have an output, but then we use a summation to recover a permutation invariant to output. So this architecture is completely system agnostic, and it does not depend on the form of the Hamiltonians. And only during optimization, the network parameters are optimized through this energy minimization principle. Okay, so here let me show you some results. So one of the first system is to look at is this interacting electrons in the 2D harmonic trap. This is a so-called quantum dot. And this problem is specified by the number of electrons and by the dimensionless interaction strength lambda. And the idea is that these objects are like artificial atoms, and the electron can feel a set of orbitals. It's a strongly interacting problem, especially when interaction is strong. And here I show you the ground state energy for several different cases. This is for 6 electrons for different interaction strength. And we can see that the results from our architecture is energy is lower than traditional methods such as Hartree-Fock, Slater-Jastrow, or even Slater-Jastrow backflow. Now, what got me really excited is that just very recently, my student team took this approach to the next level. So the true test of AI, arguably, is ability to generalize. Okay? You train a network on certain problems, and it may acquire the ability to solve unseen tasks. So in the context of this quantum dot problem, the Hamiltonian depends on this parameter, which is interaction strength, and depends on the particle number n. So by further including these parameters into the network, by conditioning these Fermi sets on the Hamiltonian parameters and particle numbers, what we do is we train a foundation model and to learn the entire family of ground states over the parameter space. Okay, and here are the results. So we train the neural network by energy minimization on 6, 8, and 10 particles for interaction strengths lambda equals 0, 1, 2, 5, 8, 10. Okay, so n equal 10, lambda equal 1 and 5 are part of the tasks that we ask neural network to do. And by energy minimization, you observe these ground state charge density in real space, which is circularly symmetric. And then we take this optimized network and we directly ask it to predict the ground state wave function for unseen particle numbers and for unseen interaction strength. For example, n equal 10, but now interaction strength 7, or for n equal 7, which is never been trained on. So without any further fine-tuning, the neural network predicts wave functions from which we computed the energy and we computed the one particle average density. And these are shown here. Okay. For n equal 10, lambda equals 7, the charge density is symmetric. For n equals 7, the charge density is not fully symmetric. Okay. And then we think about it and we understand what's going on. That for 7 electrons, this corresponds to so-called partial shell filling. In this case, the ground state has the degeneracy between unlimited L and minus L. When lambda equal to 1, the degeneracy between L equal plus and minus 1, so it's a p-wave-like symmetry. So that's why by a linear combination of p plus IP and p minus IP orbitals, the ground state density shows as twofold symmetry. But as interaction strength increases, the ground state changes from L equal 1 or minus 1 to L equal 3 minus 3. So it's like F-wave symmetry. And in this case, the network correctly predicts this F-wave 6-fold symmetric charge pattern. Okay, so prediction works on unseen particle numbers and interaction strength. And here's an energy. The network never outputs energy. It always outputs many-body wave function, and energy is computed from large-scale Monte Carlo sampling. And as we increase interaction strength, you see that these blue dots are the training data sets, and all the rest are from the prediction. Okay. And we can take this all the way to 50 electrons. And in this case, again, we train on just a few interaction strengths, and it predicts other energies for other cases. So this brings me to what we try to do in the long term. We want to really build a universal foundation model for all matter. Okay, so for any given set of nuclear coordinates, I want the foundation model to be trained and to predict the many-electron wave function. So I call this a large electron model. So if you compare a large language model and large electron model, there are clearly a lot of differences. Large language model must be learned from human-provided data, the internet texts, and the accuracy is fundamentally limited by the data quality. And by now, all the internet text probably has all been used. While for the large electron model, there is a fundamental principle behind, which is the many-electron Schrödinger equation. And based on the variational principle, the energy produced, the wave function produced is always a variational. And there's no need for any training data. The network generates vast set of trial wave functions and get optimized by minimizing energy. So in that sense, accuracy is only limited by the size of the network, by the computation resources. And they also share a lot in common that in both cases, we use a large parameter neural networks and the self-attention seems to be very powerful in both cases. And a lot of techniques from computer science in optimization, in generalization, we can benefit from. So if this is successful, we are able, then we believe that having such a foundation model can help us discover new materials to improve the design of quantum hardwares. And also, I think that the foundation model can help us improve the density functional theory. In a sense, you can think of the density functional theory as a foundation model, but it's based on a very crude descriptor, which is just the ground state density. Okay? While the many-electron wave function includes the full information, okay? And also molecular dynamics. Okay. Okay. So now in the last maybe 10 minutes, we haven't been able to use this foundation model or train on complicated materials, but we do have made some success in predicting quantum phases matter that has never been thought about before. So the problem I'm going to tell you now is this problem, this long-standing problem, which is the ground state of a uniform electron gas, just the electrons with Coulomb interaction, but no periodic potential. And this problem is interesting. It's known that at high density, we have a liquid state, a Fermi liquid. At low density, we have electrons crystallized to form a crystal. But there's a long-standing debate what occurs at the intermediate density. For example, this paper by Steve and Boris proposed some kind of a microemulsion state that's intermediate between crystal and liquid. Okay. At a finite temperature, there's a thermal version of this problem that is now well solved. And for example, as we increase temperature, as a crystal melts, it melts by proliferation of dislocations in 2 dimensions. And that leads to this exciting metal phase, exciting phase. Okay. So the problem we study is motivated by some fractional quantum Hall experiments at Princeton. We study basically electrons in quantum wells, but we take into account the finite thickness of the well. Okay, so it's a problem of a realistic device. Electrons are confined by the band gap and it's confining to this certain thickness of width d. And the finite thickness introduces another energy scale in the problem, which is, you can think of it as the energy difference between different subbands. And so in total, this problem has 2 dimensional parameters. One is the so-called the RS, the interparticle distance in units of ball radius, and the other is the thickness in units of the ball radius. Okay. So in the limit, when d is very, very small, it reduces to a purely 2-dimensional system. Okay. But here we're going to see that the finite thickness introduces a new twist. So this is the phase diagram as a function of thickness and interparticle distance. And these dots represent the structure factor at the peak. Okay. And so what this peak in structure factor indicates is the formation of crystals. Okay. So you see that at high density, and what we get is metallic states, liquid states. When the film is thin, the charge density is peaked at the middle. That's what you expect of occupying just the lowest subband. But as the thickness increases, you see this electron spontaneously form a bilayer structure, even though it's a single continuous quantum well. And this is actually known from experiments that people measure this bilayer splitting through quantum oscillation measurements. But what's interesting now I want to focus on is at the low density when electrons form crystals. So again, when the film is thin, you get a basically 2-dimensional Wigner crystal. This dark spots represent the high electron density. You can see they form a triangle lattice, as you expect for a Wigner crystal, and the inset shows the Bragg peak in reciprocal space. But as the thickness increases, you see that electrons now spontaneously form 2 layers, and in each layer they form a triangle lattice Wigner crystal. So that combine the 2 layers together, you see that the high density region form a honeycomb. The 2 triangle lattices are laterally offset. Okay. And one can understand again both cases from the classical limit. Suppose we take off quantum kinetic energy and just minimize the Coulomb interaction in this exactly same setting, we can get these type of crystals. Yes.
So I'm just confused. This is all continuum model type.
It's all continuum. Yeah.
So this is not occupation of a second subband or that kind of business.
Oh, actually, here, when you are at a larger thickness, right? Because the subband gap reduces and you have strong proton interaction, electrons actually occupy more than just lowest band. In fact, it almost occupies the lowest and next subband almost equally. Yeah, strong interaction.
Is that how I should think of that?
Absolutely, absolutely.
The second subband.
Absolutely, is strongly occupied.
Can then I map that to the crystalline case as well?
Yeah. If you want to understand some sort of at a quantitative level, yes, absolutely. So that's why I said, once neural network finds this, right? Again, the neural network doesn't know anything about the subband physics or anything. It just solved the many-electron Schrödinger equation in this setup, right? And we're using one network for all this primary space, and it just finds what's the lowest energy state. And then we analyze the wave function. We look at the density distribution. We look at the structure factor. That's what we're doing. It's like a numerical experiment. Okay. But yes, if you want to qualitatively understand all these, that's exactly the picture. Because of the repulsion, electrons like to go into two layers, and they can do this by populating the second subband. Yeah, you can think of one is bonding, one is anti-bonding.
The point is, you didn't put any of this.
No, none of this. Everything I'm doing, right? All the stuff. Yeah, this is a good question to clarify. I mean, we're just using the same architecture that doesn't know anything about the Hamiltonian. The only place the Hamiltonian enters is in this loss function, which is energy expecting value. And the neural network is always randomly initialized. So there's no physics input besides the Hamiltonian, and Hamiltonian only enters in the loss function, what is loss function? That's where Hamiltonian enters. Okay, so now, but then, well, we're really surprised that at some intermediate density, okay, at RS equal 20, okay, and the thickness equal 80, a new pattern emerges. Okay, so if I show here is the total charge density, okay, in this field of view, and it doesn't look like a crystal. But if you look at the density in the upper half of the well and the lower half of the well, you see a perfect triangle lattice. But unlike the honeycomb crystal, in here, the top and bottom layer are spontaneously 30-degree twist away from each other. Okay, so what we get is a spontaneous formation of bilayer structure with 30-degree twist, and with this 30-degree twist, we get a 12-fold symmetry. For example, there are 12 bright peaks, and no crystal can give us a 12-fold symmetry. Instead, what we get is a quasicrystal. Okay, it's a structure where there's no periodicity, but there remains high-intensity structural peaks with the 12-fold symmetry. Okay. And this is something that, at least to my knowledge, never been thought about before, the fact that the electron can form a quasicrystal. And it does it in a very simple setting of just a wide semiconductor quantum well. Okay. So that's a discovery enabled by AI. And recently, with my student, Filippo, and the student Pierre and Filippo, we want to understand this better. As theorists, like to understand this better. So in fact, in the classical limit, the interlayer coupling always favors commensuration. So the honeycomb commensurate structure is always lowering energy classically. But on the other hand, if we take into account of the quantum zero-point fluctuation, okay, the zero-point fluctuation adds an energy h bar omega k for every vibrational mode of the crystal. Okay, k labels vibration mode. In the honeycomb crystal, the two layers are locked together. So at least at long wavelengths, you have this gapped optical phonon branch in addition to the acoustic branch. And the optical phonon costs a lot of energy that increases the zero-point energy. On the other hand, if you have a 30-degree twist, there's no commensuration. The two layers can slide freely relative to each other. So it's very soft. Okay, so that reduces the zero-point energy. And here, what we show is the energy difference between the two states as a function of the inverse of the mass. The inverse of the mass controls the degree of quantum fluctuation. So in the classical limit, if we treat the particles as a point classical particle, energy should be independent of the mass, but quantum fluctuation introduces the dependence on the inverse mass. And you see that as quantum fluctuation increases, the quasicrystal wings. And this calculation, you now can do a very large system size with some hundreds or even thousands of particles. And for realistic material parameters, for holes in gallium arsenide, for example, at RS equal 20, the quasicrystal according to our calculation, you should win. Okay, so yeah, just in the last few minutes, let me give you another example. Again, it has to do with crystallization, but instead of the crystallization of Fermi liquid, let's look at the same problem, but now in a strong magnetic field. And in this case, we know that there's this the emergence of fractional quantum Hall states where the Hall conductance is quantized. And for example, a filling factor of 1/3, 2/5, 3/7, these are all fractional quantum Hall states. These are strongly correlated quantum liquids with hosting fractional charges. But on the other hand, this is a recent experiment from zinc oxide, which has a strong interaction, large effective mass, so strong Landau-level mixing. And you see that adjacent to these fractional quantum Hall states are diverging resistance peaks, and these are believed to be, again, electron crystals. And there are also a recent experiment from Yazani's group in bilayer graphene that directly images these crystals just slightly away from 1/3 filling factor. So fractional quantum liquids are described. The essence of it is captured by this beautiful wave function that Löffing wrote down. And this wave function does not look at all like a single slit determinant. When m is 3, for example, at 1/3 filling, there's no way to write this wave function into a single slit determinant. But remember, our architecture is built on slit determinants. It's based on determinants. So the question is then, can this determinant-based architecture find the fractional quantum Hall liquids? Okay. So this is what Tony did back 2 years ago. And we're basically solving this problem of 2D electron gas with an electrostatically defined area in the presence of magnetic field. And in this case, again, the neural net direct solved the many-electron Schrödinger equation without knowing anything about Landau levels. And in this problem, the interaction strength in units of the cyclotron energy defines a dimensionless parameter. And when this parameter is small, the traditional method says we can truncate the Hilbert space into the lowest Landau level, and one can perform exantization when the particle number is small. But however, this so-called exantization is not really exact because it throws away all these higher Landau levels. Well, in reality, Coulomb induction can always populate electrons into higher Landau levels. So the neural network captures all of this. And that's why you see that even for weak Landau level mixing, the neural network energy is close to the ED energy, but actually lower than it. Okay, so this again shows the accuracy of the network. One can also look at the wave function. So the Löffing wave function at 1/3 filling consists of third order zeros. So here the color represents the phase of the wave function. What we do is we take a typical sample in the wave function and freeze n-1 particle coordinates and plot the wave function as a function of one last electron coordinates. Okay, so anytime that this last particle approaches an existing particle, the wave function shows a 6 pi phase winding. Okay. However, if you look at the actual neural net wave function, we see that the third order zero all splits into 3 first order zeros. And this is exactly what you want to expect. The Löffing wave function is the exact wrong state of a short range interaction, Hamiltonian, while this is the Coulomb interaction, the realistic Coulomb interaction. So at long distance, the Löffing wave function captures the essence of fractional quantum liquid, but at short distance, we can do better. Neural network finds a better state with lower energy. And as this Landau level mixing parameter increases, you can see the neural network energy is significantly lower. Okay, and also the Landau level mixing become much stronger. So finally, when the interaction strength is very, very strong, what we expect is that even the 1/3 fractional quantum Hall liquid should crystallize. Okay, at the very strong interaction limit, the ground state is always a crystal. And this has never been seen before. The 1/3 state is particularly robust against the crystallization. But then with Ahmed, we use this again, this neural network. We find that as we increase this interaction strength, at, for example, kappa equal 20, you see the real space pair correlation clearly shows a crystal. Okay. So in this example, we see that very different phases, fractional quantum Hall liquids and the crystal, which are even topologically distinct, they can both be discovered by the neural network with the same architecture. So different states simply correspond to different values of the network parameters. And we can nail down the crystallization to onset between kappa equal 15 and 20. Okay, so let me just summarize with this plot. that with this universal architecture, I think we have a unified description of quantum matter, whether it's a metal, an insulator, a superconductor, fractional quantum Hall states, fractional chain insulators. And just to show that the accuracy of the neural network, instead of solving every problem individually by minimizing energy, in this last slide, I just want to show you a different task. We take all the human intelligence, the wave functions describing each of these phases. Again, they take very different forms. It's Slater determinant, pairwise products, BCS wave functions, right? All take very different forms. And we ask the same architecture to maximize the overlap of the neural wave function with these target wave functions. And in each case, we find extremely high overlap, up to 25 particles. We're only limited by our GPU resources. And you can see that it reaches more than, for example, 85% overlap. And this is the wave overlap between many particle wave functions. Okay. And we're only using up to about 1 million parameters. Okay, so to summarize, so I've described what we have been doing the last 2 years, which is to develop an AI model for studying matter. All matter is fundamentally quantum. So this gives us the possibility of just targeting the many-electron wave function that describe electrons with Coulomb interaction. And from that, we want to determine material properties, emerging material properties. This is made possible because we have a universal architecture for fermions. And thanks to this foundation model spirit, somehow by training the neural network on multiple tasks, on multiple Hamiltonians, it can learn the ground state across the parameter space. If we can do this at scale, we would be able to develop a foundation model for all matter, okay, for all materials. And I'm showing you some preliminary examples that the network can discover new quantum states, quasicrystals, and it can locate the transition between fractional quantum Hall and electron crystal. And with that, I'm going to stop. And thank again all my team members. And if you want to find out more, you can find our work and our public research code on the website. Thank you.
So you mentioned that in a sense, DFT is based on a very simple foundation model. Have you tried to compare the foundation models that come out of yours to DFT? Absolutely.
So first thing that the DFT, I think for a long time I've felt that this philosophy of DFT is very modern, right? Just to use a very simple descriptor, which is the ground state charge density, one particle density, right? You can get exchange correlation functionals that can be applied to all materials. Right? I think the spirit is really fantastic. Now, of course, as you know, that in reality, this doesn't work very well for strongly correlated systems. And I think the bigger problem is that the DFT method is not variational. The energy that the DFT gives you, the total energy, is not variational. It can be even lower than the true ground state energy. This is why I really want to think about the wave function-based methods.
Yeah. So, very nice talk. So if I have an electron system with a periodic potential,
right?
Does this method still?
Yeah, absolutely. So no, I didn't show it, but catch, for example, right? I mean, we solve the individual problem for electron in the periodic potential. We get, for example, Fermi liquid state, and we get generalized Wiener crystals. The crystals locked to the potential. But also, my student Catch recently developed a foundation model approach. Again, you can change the potential depths, and the network can solve all these problems at once, and then it can predict. Yeah, absolutely.
There are theorems that supposedly say in like qubit systems or spin systems that it's hard to solve for the ground state, like harder than classical computation can do in polynomial time. But obviously, whatever, in machine learning, there was similar stories about like it was supposed to be hard to learn certain things, and then for practical real world problems, it wasn't really true. Do you think that this is basically going to be the same story? Like,
yeah, this is a fantastic question. So, so one thing I will say that this universal approximation theorem, right, guarantees, and now we have a fermionic version of that universal approximation theorem. It guarantees that if you have a given system size, let's say you study 100 particles. For fixed system size, as you increase the network parameter, you can always approximate this wave function to arbitrary accuracy. Okay, so this is guaranteed by the universal approximation theorem. Now there's a different question, which is if you have a fixed size of the network, let's say 2 layers, 3 layers, right? And the question then is what kind of wave function can be represented with a network of a given size? So this is a different question which I did not address today. I think it's actually a very interesting theoretical problem. One thing I can say for sure is that the standard characterization of the complexity of wave functions, such as entanglement, does not apply here. This attention mechanism is all to all. It does not care about any spatial locality. So I think it's a very interesting theoretical problem. So young students, if they're interested, that'll be great. Yeah.
This might reflect how little I understood, but kind of related to Xiaolang's question, which is this is real space. This was jellium kind of background, probably for the quasicrystals.
Yeah.
It smells like this might be a very interesting, different approach to the disorder problem in interacting systems. So
absolutely. So
computational complexity would not be hard if you put in a disorder potential.
Absolutely, yeah. So this is exactly something we want to look into.
But that should scale much, or that should be much better than LDA type of things.
Oh yeah, for sure. Problems involving disorder, problems involving impurities, problems involving device design, right? When you have a device, let's say you want to build an anion interferometer or whatever, right? I mean, this real space-based method is extremely flexible.
Let me just comment. You just look at the beginning, and this is all done with only one GPU.
Correct.
We 3 weeks ago, we hear a very different style of talk. I mean, just a very different approach, but you can see the potential. Yes.
Yeah, thanks, Liang. So my question, how do you make sure it's the global minimum rather than the local minimum?
Yeah, there's no guarantee. People ask me, is there a possibility? Do you worry about it stuck in the local minimum? My answer is very simple. Yes, we always worry. Right? There's no. I mean, I cannot rule out the possibility of being stuck in local minimum. Now, there's one thing that helps. When you minimize the energy in continuum space Monte Carlo, when you reach an energy eigenstate, okay, not only the energy is the lowest, let's say you reach the ground state, not only the energy is lowest, but also the variance of local energy is 0. So in other words, one way to think about it is, because the many-electron Schrödinger equation is a differential operator, right? So for any particle configuration, when you reach the exact ground state, the Hamiltonian operator acting on this wave function divided by the wave function, that becomes a constant. So as you move in configuration space, you find that the local energy stays constant.
That would be true if you reached a raw. That's
also true if you reach yeah. But it is much more unlikely. Yeah. Now, in reality, of course, it's very hard to get exact constant, right? Even for very, very large network. I mean, I can show you for 2 electrons, okay? I can show you that you can literally see that variance go to 0. Yeah. For 2 electrons in helium atom, for example, energy goes to 0.
Yeah, thanks for the talk. So I wonder if there's any understanding of the limitation of this network. Like, for example, do you see examples that you like in which case you need really deep network, or you like
Absolutely.
the energy?
This is a great question. Yeah. So here I talk about a single architecture which is based on determinant, and even though it's universal, clearly it represents some states easier than others. Things like Fermi liquid and crystal, even quasicrystal. The hardest problem we encountered is what Tony did, is to study the fractional quantum Hall problem. Okay, and the optimization is highly non-trivial. You have to wait much longer, and with complete random initialization, we are only able to reach 12 particles. Again, using one GPU. Okay, one GPU. Okay, but since then, okay, but at least it worked. Okay, for 12 particles, that's how my group members all get excited and jump into this field. Now there are other ways. So for example, some of our recent work, what we did is transfer learning. You you first solve the problem for a small number of particles, and then after the network has been optimized, there are ways. We developed ways to optimize the neural network to apply it to a problem with larger number of particles, and by just then training a little bit more, you can reach the ground state. So one of the remarkable things is that the neural network method is extremely flexible. Extremely flexible. That's why this foundation model approach can actually work. And that's also why things like transfer learning, etc. can work. So really, I think that I find it amazing that network is so so powerful in generalization to generalize. Yeah.
Thanks for the awesome talk. Have you found any sort of like naive scaling relations between the number of particles that you have and then the number of parameters that are needed to get a sufficiently converged result? Is that like dimension dependent?
Yeah. So we have an empirical observation that to reach a certain accuracy, the number of parameters scales quadratically with the number of particles. But again, it's purely empirical. Okay, so nothing.
So thank you for a nice talk. So I was wondering that if you got the energy from like Monte Carlo process, so that would have fluctuations. So wouldn't those fluctuations harm those gradient descent process when you have large particle number?
So yeah, I mean, it's always noisy, right? It's optimization and noisy.
It's noisy, yes.
Yeah, it's always like that.
But wouldn't it like would it be the bottlenecks for the optimization?
So for example, if you have more GPUs, then you can increase the so-called batch size,
yes.
And this will reduce the amount of noise. And we find that that makes the optimization much better.
I see.
Yeah, much better.
It could be generalized to even more particle number.
Oh yeah. I mean, again, this is with one GPU for 50. Yeah, we've already reached like 100 particles, or no, actually 150 particles with one GPU. Yeah.
So after you trained your model, I was wondering if there's an analog to like mechanistic interpretability. Like, can you actually look at the weights of your model and learn new physics from the weights themselves?
Absolutely, yeah. These are all excellent questions. So as I said, I kind of joked that the traditional way of physics is less is more, and now we go to more and more. But I think once we use this large parameter network to get a really accurate ground state, I think we should learn how to compress. Right? We should learn to compress. Can we come up with a much more economical description of the wave function, not as accurate, but in the same phase, right? So I think that is an interesting question about interpretability.
Steve,
yeah, is there ways to parameterize a density matrix and use thermodynamic variational principles?
Yeah, that's something I'm quite interested in. Yeah, I haven't thought much about it. I'd love to discuss more with you. Yeah. I think that would be indeed very right.
Are there any prospect from going beyond the finite dimensional configuration space and applying it to quantum field theory problems, the lattice in QCD, this sort of thing?
I mean, in some sense, we're already doing that because we're dealing with continuum space, right? Actually, it's an interesting question. So, in lattice QCD, right, you discretize space, and I think that should, for solving many-electron Schrödinger equation, we work directly in continuum. To me, this is a big advantage of neural network. There are like a lot of well-developed methods for lattice systems, like the emerging tensor network, but I don't really see anything like this for continuum systems, right, with neural network. So back to your question, I think the same method could be applied to quantum field theory, because that's also in continuum space. Yeah.
Okay.
How could it be applied? Isn't your method based on having a finite number of real number of variable inputs?
Yeah. So I think indeed, in QED, this is an excellent point. So in QED, in vacuum, right, has a lot of virtual particles in it. So we might need to think in terms of some truncation in terms of allowed maximum number of virtual particles. Yeah.
Okay. Let's thank Liang again for being.